Hello everyone. So today we will understand the Gauss law. So Gauss law is one of the most important tools in electrostatics. Our goal is to not to remember formulas for electric field, but to by using symmetry, by using Gauss law, we can calculate the electric field or electric flux for any object without doing an integration. So in today's video, first of all, I will explain the physical meaning of what is flux, what is electric flux. Then we will go towards the Gauss law, and also we will see some of its applications. So let's start. First we will start with the flux. So first let's try to understand what is this flux. So what is the flux? So flux is the basically energy passing through an area. If we let's take an analogy. So flux is energy passing through an area. If we take an analogy of water, let's say this is one object with area A1, this is another object with area A2. Let's say water is flowing. Let's say water is flowing in this direction. So this object has area A1, this object has area A2. So let's say water is moving with velocity v, and in 1 second. So basically, how much amount of water or how much volume of the water is flowing through this area A1 or this area A2, that how we write, that is what basically flux. So here, how much volume of water has passed through this area A1, that we write as A1 into V. Here V is velocity of this water. So for the area A2, how much water or how much flux of water has passed through this area, that we write as A2 into V. So this is basically, this is what flux, the energy passing through an area. So this is just analogy. If we look at the electric field, so let's understand now electric flux. So in case of electric field, what is happening? Electric field, they carry energy with themselves. So let's say if we have object like this, and these are electric field lines. Let's say this surface has area A. So how much number of electric field lines are passing through this area? This is what called as electric flux. This is what our electric flux. How many number of electric field lines passing through area A? So basically we denote it with symbol phi. So basically area vector is basically normal to the surface. If you have surface like this, then area vector will be in this direction. So here we have electric field. So flux have we defined number of electric field line passing through an area. This is what our electric flux. And this flux is given as dot product of electric field and area vector. So here in this case we have considered electric field is constant, and this has surface with area A. So basically electric flux, how we define? We define as dot product of electric field vector and area vector. This when this E is constant. So this area vector into electric field vector. This also we can write as E into A cos theta. So basically dot product between two vectors. So suppose if we have area or object like this and electric field, let's say they are passing in this direction. So now area vector will be in this direction. So here between electric field vector and area vector, let's say angle is theta. So in that case, flux we can write as EA cos theta. Basically dot product between area vector and electric field vector. So this angle is between area vector and electric field vector. So let's say, so now we have seen when the electric field is constant, means for all the surface electric field is basically in same direction and it has same magnitude. So this is formula for when electric field is constant. So now if we see the another example where electric field is changing with the area or with the curve of object. So in that case, let's say now let's say we have object like this. So basically, let's say here electric field direction will be different. Here electric field direction is different. Here electric field direction is different. Let's say. So basically, what you can do in such case where electric field is variable, when electric field is variable with the area or with the curves, how we write flux? So basically, what we can do, we can take a small component. So let's say electric field is in this direction. We can take the small component of area, that is dA, and we can sum over it. So we can get the electric flux through total surface of the object. So basically, we have taken a small component of area, that is dA. So I will calculate here flux and I will sum over it. Sum over it means basically we have to do integration. So integration electric field into dA. This dA is small area here. So sum over it basically means integration. If we do integration, then we will get flux through the total surface. So this is when E is variable with the surface or basically with the curves. This is our formula for flux. So physical meaning of this flux is the amount of electric field lines passing through an area or the amount of energy passing through an area. As electric field itself, they carry energy with themselves. Okay. So this flux is scalar quantity. This flux is scalar quantity and it has magnitude Newton meter square per coulomb. So these are SI unit of flux and it is scalar quantity. So now let's go towards the Gauss law. So now we have understood the physical meaning of electric flux. So electric flux is basically energy passing through an area. So now we will go towards the Gauss law. So Gauss law, what is the statement of Gauss law? So let's say there is closed surface. This is closed surface. And let's say closed surface means 3D objects like sphere, cube. So let's say inside there are charges Q1, Q2, Q3, and let's say outside Q4, Q5. These are Q1, Q2, Q3. These are charges inside this closed surface, and this Q4 and Q5 are charges outside this closed surface. So, what is this Gauss law says? Gauss law says that the flux through an closed surface is given as total charge inside this closed surface times 1 upon epsilon naught. So what is this Gauss law says? This Gauss law says that flux through and closed surfaces. So we write it like this: closed surface integration E dot dA. This is our flux. So flux through and closed surface. This is equal to charge enclosed inside this closed surface times 1 upon epsilon naught. So total charge inside upon epsilon naught. This is what our statement of Gauss law. That means flux through and closed surface is total charge inside this closed surface times 1 upon epsilon naught. So one thing we have to remember here, let's say through this point we are calculating flux. So due to this Q1, this will be our electric field line. This is Q2, this is Q3. So now due to Q4 also due to Q5. So here one thing we have to remember, this this E here. So flux how we write? Integration of. So here this electric field is net electric field. That means electric field due to all charges. So charge Q1, Q2, Q3, Q4, Q5. E net into dA is equal to, so Q inside here. So this Q inside means only charge inside this closed surface, not outside charges like Q4 and Q5. So here E net, that means due to Q1 we have electric field E1, due to Q2 we have electric field E2, due to charge Q3 we have electric field E3, same way E4, E5. So this electric field is net electric field due to all charges. So flux will be equal to, so integration of E1 dA plus E2 dA plus E3 dA, E4 dA plus E5 dA. So here now if we see the flux through the charges, so here now if we see the flux through the charges, so basically this Q4 and Q5 are outside these closed surfaces. So flux due to this outside charges will be 0. So why 0? Because this electric field line will pass through the one point and it will go outside through the one point due to this outside charges. So due to these charges Q4 and Q5, flux will be 0. So from Gauss law we know that E1 dA, I will write Q inside upon epsilon naught. So basically E1 dA, that means Q1 by epsilon naught. E2 dA, that will be equal to Q2 by epsilon naught. Same way Q3 by epsilon naught. And due to these two charges, flux will be 0. So my net flux will be now, net flux will be Q1 summation of Q1, Q2, Q3. So this Q1, Q2, Q3 are basically charges inside these closed surfaces. So this will be equal to Q inside upon epsilon naught. This is what our Gauss law. Flux through a closed surface is given as total charge inside closed surface upon epsilon naught. So now let's see some applications of this Gauss law. So let's take one example. First, we will take one example. So we will understand how to find the electric flux. Let's say we have this open surface. Let's say this is closed surface. Here we have charge Q here. Here we have charge Q, and here we have charge Q outside. So these are three hemispheres. So this is open and these two are closed. So this part we will see later. So first of all, these two are closed surfaces. So for this hemisphere, flux how we can write? So from the Gauss law, flux we write as charge inside this closed surface upon epsilon naught. So this Q is inside these closed surfaces. So basically flux will be Q upon epsilon naught. Now for this surface, here this Q is outside the surface. This closed surface we have, but this charge is outside this surface. And as we have seen, due to outside charge, electric field will pass through one point and it will go outside through the one point. So due to this outside charge, flux will be 0. So now for this part, this hemisphere is open. So basically Gauss law we know, for any closed surfaces charge inside upon epsilon naught. So here we can do one thing. So we have this hemisphere. Our charge Q is here. So what I can do? I can draw complete sphere. So for the complete sphere, if charge Q is inside that sphere, so for this complete sphere, how we write? We write as Q upon epsilon naught. But now we have what here? So for closed or complete sphere, we write as Q upon epsilon naught. But here we have only half part of it. So due to symmetry or by symmetry, the flux will get equally divided. That means for half part, flux will be half times of whatever the flux is for this total sphere. So Q upon 2 epsilon naught. This will be the flux through this hemisphere. So we will see one more example. So we will take one application. Electric field due to long infinite wire. So let's say we have wire. So this is infinite wire. So let's say the charge distribution on this wire is basically, let's say, lambda coulomb per meter. This is charge distribution on this wire. So now how we can find the electric field due to this long infinite wire? So Gauss law we know. Gauss law how we write? We write as E dot dA q by epsilon naught. So here we have this long infinite wire. So important thing is what we can do. We can draw a Gaussian surface. So here charge distribution on this wire is lambda coulomb per meter. So lambda means basically we know that will be q by L. So L will be length. So let's draw Gaussian surface. So this wire is of cylindrical shape. That's why we are drawing cylindrical Gaussian surface. So this is our Gaussian surface. Let's say this is radius r, and let's say this length is L. So now electric fields lines will be like this. Due to this wire through this surface, electric field lines will be like this. So now we know E dot dA is q by epsilon naught. So now here area is this one area, that is curved area. For this cylinder, for the cylindrical Gaussian surface, there are two areas, that is this curved part and this flat. So now if we look here, electric field lines are in this direction. So for this curved surface, if we look at this curved surface, for curved surface, electric field lines and area vector are basically parallel for this curved part. So this electric field parallel to the area vector for this curved part. If we look at the flat part, here electric field lines, and so now area vector for this flat part will be in this direction. So basically angle between this area vector and electric field is 90 degree. So for this flat surface, electric field is perpendicular to the area. So as we know, if electric field is perpendicular to the area, that means angle between them is 90 degree, and cos 90 degree is 0. So basically electric field will be 0, or flux will be 0. So now we have only one part, this curved part. So for this curved part, at every point electric field is parallel to the area. So, and as we know what is the area, so E dot A, how we can write E dot A. So A area for this curved part, that is what, 2 pi r L. This is length L, this is radius r. So now we can write the electric field. So due to this flat surface, electric field will be 0 because they are perpendicular. So now we have E dot 2 pi r L and charge inside upon epsilon naught. So here charge means lambda into L. Lambda is linear charge distribution, so that will be lambda L by epsilon naught. So here L will get cancelled. So electric field what we have, that will be equal to lambda upon 2 pi r epsilon naught. This is what electric field. If we multiply and divide by 2 on both sides, we will get E 2k lambda by r, where k is our 1 upon 4 pi epsilon naught. So this is how we have found electric field due to long infinite wire by using Gauss law. So Gauss law helps us to find electric field without doing an integration. Here we have not done integration. By using just symmetry, here we have taken this cylindrical symmetry. So this symmetry helps us to find the electric field by without doing an integration. So basically, one thing we have to remember about the Gauss law. So we have seen that for any closed surface, Gauss law says that for any closed surface, flux will be charge inside upon epsilon naught. So for any closed surface, that means, let's say if we have sphere, let's say we have cube, let's say we have some arbitrary shape. So size and shape of object doesn't matter. We are saying for any closed surfaces, means as long as the surface is closed. Let's say here we have Q, here we have charge Q, here we have charge Q. So this object, these three objects have different shape, different sizes, but still by using Gauss law, flux will be total charge inside upon epsilon naught. So this doesn't depend upon shape and size of the object. And one more thing we have to remember, is this Gauss law applicable everywhere? So answer is yes, this Gauss law is applicable everywhere, but in cases of high symmetry, it is easy to find this flux by using Gauss law. Gauss law is applicable everywhere, but only in cases where we have high symmetry, it is easy to find this flux. So basically that's all. So we have understood the Gauss law, physical meaning of Gauss law, what is flux, and we have also seen one application. So this Gauss law is one of the most important tools, because without doing an integration we can find the electric field here. So that's it. Thank you.